we're going to cover MCMC sampling, Markov chain Monte Carlo, as well as optimization method, okay? In module 3, what we saw is how can we perform Bayesian estimation. Markov chain Monte Carlo is what's going to allow us to bring these Bayesian estimation for complex and any generic problems, okay? And what we're going to see as well is that the Markov chain Monte Carlo, MCMC, has some parameters that needs to be tuned. We can tune those parameters using optimization method. And in a second time, we're also going to see that actually we can make approximation to the Bayesian estimation problem using those same optimization techniques as well. So this is what we're going to cover today. If you want to use a reference, it's going to be chapter 5 and 7 in the book Probabilistic Machine Learning for Civil Engineers. Okay, so in introduction, what we're going to cover here in the first part is the method we can use to estimate the parameters theta. Okay, this is what we saw not in module 4 but module 3, where we were trying to obtain our posterior PDF for the parameter theta given the data. Okay, to obtain this, what we did is we multiply the likelihood of observation conditional on the parameters times my prior PDF for those parameters divided by my normalization constant, okay? But what we saw in module 3 is that it was intrinsically really hard to calculate that evidence or that normalization constant because it involved an integral, which is often in a very large dimension because we have many parameters we want to estimate simultaneously. So that was problematic because we were taking samples in my prior distribution, which might really be containing little information. So might be really, the probability content might be much more spread than in my posterior. The consequence of this is that many samples are going to be wasted. They're not going to be located in the region where we have a high probability content, okay? So the consequence of this is that this approach might not scale to more complex problem with more dimensions. So what we're going to see in this module is how can we use MCMC, Markov chain Monte Carlo, to bypass the need to calculate this normalization constant. What we're going to do instead is directly take sample in that unnormalized posterior, what we have on the numerator of our Bayes rule. So the key property of MCMC, Markov chain Monte Carlo, is that it allows us to obtain sample from an unnormalized posterior, where what we're going to say is that this density of a sample we're going to take with MCMC are going to be proportional to the posterior. In this case, we're going to call this posterior or target distribution, the distribution we want to take samples from. Okay, and in a second time, we're going to see as well gradient-based optimization method, where our goal is going to be to identify what is the most likely or what are the most likely parameter value from an unnormalized posterior. So imagine that we want to find what is going to be the max of this unnormalized posterior, the summit of that distribution. Okay, so in terms of naming, where does it come from? What does it mean, Markov chain Monte Carlo? Okay, the first thing is the Markov hypothesis, which says that given the present, the future is independent from the past. Okay, what does it mean? In our context, it means that if we start from a current position that we're going to represent by the random variable x of t, which is distributed like this probability distribution, we can transition to a new position xt plus 1 using a transition function, okay? That tells me what is my probability of ending in a position x at time t plus 1 given my current position xt. And here, that Markovian hypothesis will allow me to represent that transition model that only depends on xt and not on all the previous position I were in the past. So it means here the conditional probability that depends only on xt is equal or is equivalent to the conditional probability that will depend on all the previous position I've seen in the past. Okay, this is key here because it greatly reduces the complexity of defining that transition model. So here, a Markov chain is defined as the joint distribution for all the position I would have visited over time. So my joint probability for all the position I have visited from x1 up to xt is going to be given by the product of probability of x1 times probability of x2 given x1 times probability of x3 given x2, where you see that here we build our joint by the product of a marginal and conditional, but each of those conditional only depends on one variable. So we can generalize this by saying my joint probability distribution is going to be the probability of being in x1 times the product for all t equal to up to capital T of those conditional probability, where I have only one term on the right of the conditional. Okay, how does this MCMC is going to work? Okay, so what we're going to do with that Markov chain Monte Carlo is that we're going to randomly walk through our parameter space. Okay, so what does it mean? At the end of this random walk through my parameter space, the fraction of time spent in any region of that parameter space is going to be proportional to the unnormalized posterior I'm trying to take sample from. Okay, here's an example where you see underlying the samples I've taken. This is the contour of my unnormalized posterior. Okay, this is a simple example where I have only theta 1 and theta 2. I started from the location indicated in red, and I have done a random walk through that domain. Okay, and at the end, the fraction of the time spent in any region of the domain is going to be proportional to my unnormalized posterior. Okay, so the unnormalized posterior has higher value here. I have taken more steps here. So what we're going to see with MCMC is what are the steps that are required so that my random walk generate this property where the fraction of the time spent is proportional to my unnormalized posterior. In the second time, what we're going to see is gradient-based optimization method. Okay, in this case, with gradient-based optimization method, we don't want to sample the entire posterior. Okay, what we want to do is only to find the maximal value. So we see from the contour, the maximum is at the blue point here. What I do is I can start at this point here, and I just want to go with as few steps as possible. I want to identify where's the max. And here, keep in mind, this is valid for both the MCMC and gradient-based optimization. We're going to see a lot of simple one-dimensional or two-dimensional example to illustrate what's going on. But at the end, you don't need sampling in 2D. You don't need a gradient-based optimization in 2D, okay? Usually, you're going to apply this to problems that have dozens, if not hundreds, if not thousands of dimensions. But what I want to see with you is how does these methods work so that you can build an understanding how it works, an intuitive understanding of what are the pitfalls, the limitations, the capacity, so that when you apply it to problems that are in 100 dimensions, 1,000 dimensions, 1,000,000 dimensions, you have a correct understanding of what's going on and you can safely apply and use those methods. Okay, so in this case, we're going to find the most likely value for unnormalized posterior, and we're going to see two types of methods, either first or second order methods that will rely either only on the first and second derivative of the function I'm trying to look to seek the max for. Okay, so what we're going to see, the intro, this is what we covered. The first MCMC method we're going to see is the Metropolis sampling algorithm. This is the most basic one. Then we're going to see there are some little caveat, and we have to be careful about some aspect regarding the convergence of our MCMC sampling. Then we're going to see that this convergence is highly influenced by the proposal PDF we choose in order to perform our random walk. At the end, we're going to see that we can tune this proposal using gradient-based algorithm. So we're going to see gradient-based algorithm for two purposes. One is going to be to tune our proposal PDF in the context of MCMC. This is why I'm seeing here with you. But we're going to see as well that we can use those gradient-based algorithm in order to, on its own, make a crude approximation of Bayesian estimation. Okay, why would we want to use a crude approximation? Because sometimes we cannot afford to do MCMC because it's too computationally expensive. So we might have that crude approximator that's going to work well in case that are too complex, too computationally demanding to sample using MCMC. And finally, we're going to see that for both MCMC and gradient-based optimization, we might run into some efficiency problem when we're dealing with parameter domain that are not unbounded, that are not defined in the real space. So in that case, what we're going to see is that we can go around those difficulties by transforming our sampling space. And finally, we're going to look at a complete example where we can put all these notions together. So we're covering here module 4, where we're seeing MCMC sampling as well as Newton, which is one of the gradient-based optimization algorithm we're going to see together here. Okay, let's start with MCMC and the fundamental technique, which is the Metropolis sampling. Okay, we're going to see an introduction. Where does it come from? Then we're going to see the 1D formulation. So we're going to try to estimate the posterior or take sample from the normalized posterior in a one-dimensional case. Then we're going to extend the methods for two-dimensional case. And then we're going to see once we have those samples, what do we do with those samples? What do we want to extract from what we obtain here? And finally, we're going to extend this Metropolis algorithm to the Metropolis asking, okay, which allow us to generalize what we're going to see with Metropolis to non-symmetric proposal distribution. We're going to see this in due time. Okay, history, where does it come from? The Metropolis algorithm was developed during the Second World War while working on the Manhattan Project. This was the atomic bomb that was developed at the Los Alamos laboratory. So I tell you upfront, this is not the most efficient algorithm, yet it is simple and a general MCMC method. Okay, this is not the state of the art, yet it's fundamental to understand this method if you want to later use one of the more advanced methods, such as the Gibbs sampling, the slice sampling, or what is currently the state of the art, the Hamiltonian Monte Carlo, which will really allow you to use MCMC sampling in a very large dimensional space in a reliable way. So the Metropolis algorithm, okay? So how does it work? We start from an initial state, okay? From theta 0, where here what we have is the first parameter, and the second in this means that I'm my MCMC step 0, okay? Second parameter, step 0, my pth parameter, step 0. So this is my vector of parameter I'm trying to sample, and I'm here at my initial state. Then I need to define a target distribution, okay? F tilde represent my target distribution, the distribution I want to sample from, okay? In the context of Bayesian estimation, that target distribution is going to be my unnormalized posterior, which is the product of my likelihood and my prior for the parameters. So this is the unnormalized parameter we want to take sample from. Then I need a proposal distribution. That distribution will control my random walk. So the characteristic of this proposal distribution is that it must have a non-zero probability to transit to any state in the target distribution, and it must also be symmetric. It means that so Q is going to be my proposal distribution. This is going to be a conditional probability that if I'm at position theta in my parameter space, the probability of moving in a new position, theta prime, okay? And the probability to move from theta to theta prime must be equal to the inverse, which is while I'm at theta prime, coming back at theta, okay? So given two position, the probability to go from one location to the other must be equal to the probability of being at that other position and coming back to the initial position. So a generic proposal distribution that will satisfy these two conditions would be the normal distribution, which is non-zero over the entire real space and which is symmetric, okay? In that case, we could use that normal distribution, which would be centered, so having an expected value equal to the current parameter value, and variance sigma q square, which is a parameter that will control the dispersion of that distribution, which will in turn control how big are my step in my random walk. So I can do this in one dimension. I could do this in 2 dimensions, okay? Where here now I have the mean vector, which is my current position theta, and a covariance matrix that control how big are my step with respect to each dimension in my problem. And I can generalize this in a n dimension problem. So let's look through an example. How would the Metropolis algorithm work? Okay, what we have on the leftmost graph is a representation of my target PDF. So this is my target PDF for a one-dimensional problem. This is my unnormalized posterior. And my goal with MCMC is to draw a sample from that unnormalized distribution from which I don't have access to the normalization constant, so I cannot just take samples into it. And I don't have an analytical formulation for it. So I can evaluate that target PDF at any point, but I don't know its formulation, okay? Or more, I cannot compute the quantity. That's why I need to take samples from it. And here, keep in mind that the MCMC is not to draw a sample in the one-dimensional problem, because here I can really I could calculate my normalization constant. I could draw a sample from it. And the reason is I can even plot this target PDF, okay? But what we want to look at here is what are the fundamentals of how MCMC work, so that then you can apply this method in much larger dimensional space where you cannot even think about plotting that target PDF, okay? So this is what we have on the leftmost graph. Here, the blue bar is our current sample, our current position. So the height of the bar would represent the target function, so on our normalized posterior, evaluated at the current sample. The orange bar, not the orange, the pink bar, which represent our proposed location, okay, where we want to do our random walk, the next place we want to move at. And then what we have on the other graph, on the horizontal axis, so here, horizontal axis would be the parameter value. Here on the second graph on the right, the horizontal axis would be the number of samples I've taken. So 0, this is my initial starting point for my chain. So here I want to move to my first sample. And how do I move to a sample? Through a proposal distribution. So what we have in yellow here, this is my proposal distribution, which is centered on the star here, which is my current location, which correspond to the location of that blue bar here. So this vertical axis is also the parameter theta, which correspond to that same axis here. But the negative value at the bottom, the positive value at the top. So the 5 is the 5, the -5 is the -5, okay? So I take a sample from that proposal. That sample turned out to be that right next to it, that pink dot, okay? So my current location theta is 1, okay? The blue point is at theta equal 1. And the target value here is at point 14. My new point where I propose to move is located at theta prime equals 0.9. So I move a little bit downward, a little bit to the left here. And now I look at what is my target value for this position. It's going to be 0.147, okay? You see, it's a little bit greater than what I had before. So what I'm going to look at now is a ratio alpha. Okay, so in this case, my alpha is the ratio of my target distribution evaluated at theta prime divided by my target distribution at the current location. And in this case, that ratio is 1.045. Okay, that ratio here is greater than 1, meaning that my target value at theta prime is greater than at theta. So in terms of MCMC, it means I'm always going to accept to move whenever my proposed location has a target value that is greater than at my current position, okay? So whenever your alpha is going to turn out to be greater or equal to 1, you're going to accept to move to that proposed location. So alpha is greater than 1. I'm going to say my next sample location, my random walk, is going to be the proposed point theta prime. Perfect. So I move to that new point. My new point here, it was 1. Now here it's 0.9. So my current location is 0.9. I take another sample in my proposal distribution, which is now centered around my 0.9, my current location. My new target function evaluation, my current position is 0.14. I propose to move at this point, which is at theta equal minus 0.54, where my new target value is 0.16. The ratio is going to turn out to be greater than 1. Perfect. Ratio greater than 1. I accept to move. So in this case, my new point theta s plus 1 is going to be my theta prime. Perfect. I repeat that again. I propose a new location. So now notice my current location was here, and now my new location is located a little bit below. So if my target is a little bit below, like this, I go from 0.17 to 0.15. I'm not directly going to accept to move because the location is at a lesser target value than my current location. So with the Metropolis algorithm, you're only going to accept to move to that lesser target value location with probability equal to the ratio of the two target value. So my new target value is 0.49. My former one was 0.69. So that ratio is equal to 0.87. So it means I'm going to have a 0.87 probability of moving to that new location. How do I decide if I go or not? Okay, what I'm going to do, I'm going to draw a sample U that's taken from a uniform distribution defined in the range from 0 to 1. Okay, so if the sample 0.66 turns out to be lesser or equal to my ratio alpha, I'll accept to move. If it's above my ratio alpha, I'm not going to accept to move. Okay, so for instance, in that case, since U is taken from a uniform distribution in the range 0 to 1, there's an 87% probability that is going to be lesser than 0.87. Okay, so by always checking if U is going to be lesser than alpha, I'm going to assure that I'm going to move according to the Metropolis algorithm criteria, which is to move with probability that is equal to my ratio alpha. So here, U is lesser than alpha. Perfect. My theta s plus 1, my new sample, is theta prime, the one I propose. Okay, I continue. New proposal. I'm greater than I was. I accept to move. And I continue like this. Okay, so now let's try to see what's going on. I've taken 25 of those steps, and I will draw an histogram for all the parameters values I visited. So the true target function is the red one, okay, my unnormalized posterior. And if I try to draw an histogram of the position I visited, this is what I have in blue here. So I didn't really explore well my target PDF. Okay, so what I'm going to do, I'm going to increase to 50. Okay, my approximation is not really good. What about 100? Okay, it gets better, but it's not yet a good exploration. What about 200? What about 400? What about 800? So you see that as the number of samples increases, I'm getting a better and better approximation of my target PDF. Okay, and this is the principle behind Markov chain Monte Carlo, is to explore through sampling like this. So, okay, with Metropolis sampling, what we're going to do, we're going to look step by step at what's going on in order to further describe what we saw through the example in the previous slide. So the first step is going to be to define what is going to be our target PDF. So the distribution or the function we want to take sample from. In our case, with Bayesian estimation, is going to be our unnormalized posterior. We need to define ourselves a transition probability. So in this case, it could be a multivariate normal that tell us where to move next given our current position, and S, a number of sample we want to draw. So in this case, we're going to initialize are sampling at a given location. And initially, our set of sample is going to be the empty set. And now for all the sample S in my set going from 0 to S minus 1, my number of sample, I'm going to say, okay, my current location is going to be theta S. So now my sample set is 0. So I'm at my initial location, theta 0. Then I'm going to sample from my proposal distribution. Where do I propose to move next from my current location? So I'm going to take a sample in that distribution. I'm going to compare, or I'm going to calculate the ratio of my target PDF at my proposed location versus my current location. And then I'm going to compute R, okay? The R is the minimum of either 1 or alpha, okay? Then I'm going to take sample U drawn from a uniform distribution in the range 0, 1. And I'm going to say if U is lesser or equal to R, then I'm going to say my new sample is going to be actually the sample theta prime that I propose here. If this condition is not satisfied, I'm going to say my new sample is actually the current sample. So my next sample is I'm staying at the current position. I don't accept to move to the position that was proposed here. And then I'm going to augment my set of sample with the current sample S theta S plus 1, okay? And I'm going to loop this over all my sets of samples. And here, keep in mind, when you reject the move, it's not that you're going to make some trial until you accept. No, it's really that your next sample is going to be the same sample as the current one. Okay, so let's extend this principle in more than one dimension, okay? In this case, what we have as the thin line contour are going to be my target PDF. What we have here is going to be my proposal distribution. This is my starting location. My proposed sample is going to be the pink circle, and my current sample is going to be that little star. Okay, so I'm at sample number 0. My current location is 1, 1. My target value is 0.0067. I propose using this two-dimensional proposal PDF to move at these coordinates in my parameter space, okay? Where my target value, which is represented here, so these contour and this surface represent the same thing, okay? So the new function value is 0.01. I'm greater than this, so my ratio 1.48, alpha greater than 1, I'm going to accept to move there. Then I'm here, I propose to move there, okay? Now if I compare my target value, now I'm at 0.10, okay? So the probability to move there is 10%. I draw my uniform, I draw a sample from a uniform distribution. It's going to be 0.93. This is greater than alpha. I won't accept to move there. My next sample is going to remain the current one, okay? And I keep doing this, always the same principle. So there's no difference between the 1D and 2D, except that now I'm sampling in a joint distribution for my proposal PDF, okay? So this is what we would obtain after 100 samples, okay? So you can see here, I haven't explored at all the second peak here. I need more sample, okay? With 500 sample, it gets a little better. With 1,000, with 10,000. Okay, we can really see here that the density of points is going to be proportional to my target PDF we have here. So the higher is the target probability, the more samples we're going to see, because the random walk is going to end up in those regions more often. So, okay, now that we've seen how can we take samples from our unnormalized PDF, how do we use these samples? What do we do with them? Okay, so theoretically, it could be possible to calculate the normalization constant, okay? The integral of our unnormalized posterior for all the values theta. We could do this by 1 over the number of samples, the sum of 1 over my likelihood for each of those samples, the inverse of all this. But I really advise you against using this. In practice, it leads to a very poor performance. So you cannot really rely on this to calculate the normalization constant. So, but the good thing is that with MCMC, we don't need to rely on the normalization constant. We might need it for more advanced like Bayesian model selection, but in the context of estimating our posterior for a parameter, we don't need the normalization constant. This is the whole purpose of MCMC. So what we can do instead is to use our sample in order to calculate what is going to be my expected vector for my parameters for my posterior. Okay, this is to be the weighted integral of my parameter values times the posterior density. Okay, and in practice, the key part or the key aspect of MCMC is that you can do this task very easily. So knowing that the samples you obtain theta s are all drawn from the posterior distribution or the unnormalized posterior. It means that at the end, you can obtain the expected value for your posterior as simply taking the empirical average of your sample. So 1 over s times the sum of all your sample values. This is the same thing. If you want to obtain your posterior covariance, what do? You're simply going to calculate the empirical covariance for your samples, where these expected posterior values are going to be already approximated here by your empirical average for your sample. So once you've obtained your sample with MCMC, it is trivial to calculate the expected value of your posterior, the covariance, the empirical covariance matrix as well. Another thing you might want to do is to obtain the summary statistics, so expected value and covariance for some posterior predictive estimate. So meaning, for instance, in the case where x is a random variable described by here, its PDF is described by f of x given theta, so a vector of parameters. So we can obtain the joint for x and theta by multiplying that conditional PDF or the PDF for x conditional on its parameters times the posterior PDF for these parameters. Okay, this is what we saw in the module 3 when we were exploring Bayesian estimation. Okay, so here what we want to do is to marginalize from this joint the parameter theta by integrating over those. So we can do that trivially with MCMC. So how we're going to do? So for each sample theta s we have, okay, these are samples from our parameter thetas. We're going to use each of those samples and use them to define our PDF for x. And then for each instance, what I'm going to do, I'm going to draw a realization xs from that PDF, which are using a specific value theta s. Okay, then at the end, if I want to compute the posterior expected value for x, I'm just going to calculate the empirical average of all my simple xs. If I want to calculate the posterior variance of x, I'm going to just at the same time calculate the empirical variance of my samples xs, where this expected value was approximated here by the empirical average. Okay, so once we have obtained our sample with MCMC, it is trivial to derive the summary statistics such as posterior mean, posterior covariance, posterior predictive mean, posterior predictive covariance. Other thing we might have to do is that we've quantified our posterior for our parameter, but then we want to use these parameter in another deterministic function that could be z equal h of theta, where h could be any function. That could be a complex model, as it could be something as simple as sine of theta. Okay, I want to propagate through my model sine what is going to be the uncertainty in the output of that function given the uncertainty in my parameter theta. So in that case, we do the same thing. For each realization of my MCMC samples, I'm going to evaluate my function for those samples. And these are going to be my zs. And then if I want to obtain the expected value for z, for my posterior predictive mean is going to be the empirical average for all my samples ZS. For the variance, same thing. I'm going to calculate my empirical variance for those ZS. Okay, that was for the core principle for the Metropolis algorithm. Okay, now you're going to see very often in the literature, we're going to refer to the Metropolis-Hastings. Okay, the Metropolis-Hastings algorithm is a simple extension over the Metropolis algorithm in order to deal with situations where we have non-symmetric transition probability. Okay, one requirement we define at the beginning of the Metropolis algorithm is that we need a proposal distribution that is symmetric, which is going to have the same probability of moving from one location to the other than the probability of coming back to our initial position. When this is not satisfied, we need to use not the Metropolis, but the Metropolis-Hastings algorithm. Okay, when could that happen? For instance, if we're trying to explore a parameter domain for some things like the standard deviation. Okay, standard deviation is only defined in the positive domain. Okay, in that case, we might want to rely on proposal PDF that are truncated Gaussian. Okay, in this case, that are not going to be defined for negative value. But keep in mind, the PDF we're going to use always have to be valid PDF, meaning they're going to integrate to 1 if we integrate over the entire domain. But since I have a larger chunk of the tail that was truncated here, I need to raise the probability for all the other outcome in order to ensure that my integral over the whole domain is going to remain 1. So for instance, the result is for this example, if I want to look at what's the probability to go from a current position theta to a new position theta prime, this probability density of that outcome is given by the height of my blue function here. Okay, but if I'm at my new position theta prime, the probability density of coming back to my value theta is lesser than my original value. Okay, so I don't have that symmetry anymore. So the probability of going from one location to the other is not the same as the probability of coming back. So in this case, we would need to use Metropolis-Hastings. And in the special case where we have that symmetry, if we use Metropolis-Hastings, it's going to be equivalent to using the Metropolis algorithm. So for the Metropolis-Hastings algorithm, the initialization of the algorithm is exactly the same as what we had for the Metropolis algorithm. The only difference here is that when we compute alpha, or ratio of the target PDF at the proposed location versus the current one, we need to multiply this ratio by the ratio of the proposal PDF for starting at the proposed location and landing in our current location, divided by our proposal PDF of starting in our current location and landing in the proposed location. Okay, that ratio is going to take into account the fact that my proposal PDF is non-symmetric. Okay, and the rest of the algorithm for Metropolis-Hastings is identical to the Metropolis. So the only difference between Metropolis and Metropolis-Hastings is really in that correction factor that takes into account that the proposal PDF is not symmetric. So there are some issues that were overlooked so far with respect notably to the convergence. Have I taken enough sample so that the samples I've taken from my MCMC sampling are really stationary sample that really represent samples that are proportional to for which the density is proportional to my unnormalized posterior. Okay, to look at this, we're going to look at the concept of the burning phase, where we want to see what is the impact of where we initialize our chain. Then we're going to see how can we monitor the convergence? How can we measure, have I taken enough samples? And finally, we're going to look at this through an applied example. So first, we're going to illustrate the concept of the importance of initialization through an example that you can find in Murphy, okay? In this book is from Machine Learning, a Probabilistic Perspective. So what you see here is an example of a stochastic process. In that stochastic process, we start at step 0 at an initial location. Here my initial location is x equal 10. And that stochastic process is defined so that between each time step, I have a probability of 0.5 of moving from one position to the left or one position to the right. Okay? So here I'm at 10. At time 1, I'm going to be either at 10 minus 1, 9, or 10 plus 1, 11. Okay? For sure, I'm not going to remain in the current position. So if I have a 50% chance to be at either location, at time t plus 1, if I'm here, I'm either going to move to the left or I'm going to move to the right. If I'm here, either going to move to the left or to the right, meaning that I'm going to end up being twice as likely to have come back to 10 versus either at 8 or 12. Okay, and that carries on forward in the future. And what I want you to notice is that it takes a while. So I have 1 iteration, 0 iteration, first, second, third, after 10 iteration, 100 iteration, 200 iteration, and 400 iteration. And what we can notice is that it takes a while for this problem to forget where it started from. Okay, so in that case, even after 100 iteration, I haven't reached a stationary distribution where all the probability of being in any position are equally likely. Okay, because the starting locations still have a greater probability of occurrence just because we started from there and we haven't explored enough the entire domain. So after roughly between 200 and 400 steps, I can say I cannot identify where did I start my problem from. Okay, if we would start from another location, same thing. We see that it takes several hundred steps to forget where have I started from. Okay, and so this is crucial not to stop sampling when we would be in such a situation. Okay, why? Because at the end, we're not going to be having samples that are representative of the stationary distribution. Okay, we're going to have samples that are influenced by where did I started my chain. So this is the same thing with our MCMC sampling. What happens is if you take a sample, especially if you take a sample that starts, or if you start your chain in a region of the domain that has a really low probability content, okay? It's going to take several samples in that very low probability content to reach the part of the region where you have a significant probability content. That means that this start of the chain should be discarded, okay? Because in practice, the probability of sampling this region is extremely low. So the frequency you have in that part of the domain is not representative of the sampling distribution you have for this target PDF. Therefore, what you need to have is, at the end, the samples you have, in order to be valid, they need to be taken from the stationary distribution, okay? And for that, they need to have completely forgotten where you started from. And to do this in practice, a simple heuristic is to say, for all my samples that were taken before reaching that stationary distribution, I'm going to discard them, okay? And that discard step is what we name the burn-in phase, okay? In practice, a heuristic is to say, for each change of sample, in order to be conservative, I'm going to discard the first half of my chain. So if I want to have 100 samples, I'm going to take 200 samples. In the first 100, I'm just going to discard them, okay? In order to make sure that I'm never in such a situation where I have initial locations which are disproportionately represented in my sample in comparison with their target PDF. So then how can we monitor, is 100 sample enough? Is 1,000 sample enough? Is 100,000 sample enough? Okay? If we want to do that monitoring for convergence in one dimension, this is fairly easy to do because you can directly plot your chain and look, is it roughly stationary by looking at the sample. But when you're going to be in 2 or more dimension, it's really much harder to look at, okay? Because might have dependency between your dimension. It's going to be harder to evaluate. So in that case, one thing you can do is you're going to sample multiple chains between 3 and 5, which all going to have different starting location theta 0. And then what you're going to do is you're going to compare the variance of these chains within each other, or between the variance within each chain and the variance between your chain. And this is systematized into the estimated potential scale reduction, EPSR. And at the end, the second thing you need to look at is what is going to be your acceptance rate. Okay, what is the ratio between the number of time you accept to move to the proposed location divided by all the samples you've taken? Okay, in 1D, you should aim roughly for an acceptance rate that is denoted by beta of 40%. In 5 or more dimension, that acceptance rate that leads to the fastest convergence rate is roughly 25%. But be careful, you should not be aiming for exactly 40 or exactly 25, okay? As you can see here, in terms of what is going to be the relative speed of convergent with respect to the acceptance rate beta, okay? The optimal, this is the case for more than 5 dimension. So the optimal value is roughly at 0.25, okay? But we see that we don't have a catastrophic drop in performance even if we go at 0.10 or if we go at 0.5, okay? All these values are still going to be quite efficient, okay? So you don't need to aim exactly to be at 0.25, especially that this study was made for the Gaussian posterior, okay? Your posterior might look something different than the Gaussian, so the exact optimality might not be at the same point. Where you want to avoid being is having an acceptance rate of, say, 3 or 5%, or having something around 80%. So if you accept 80% of your move, you're going to be inefficient, okay? Theoretically, your results are still going to be good, but you're going to need so many more samples to really be confirmed that your sample are taking from the stationary distribution that you're going to be highly inefficient, okay? So let's formalize the nomenclature for our sample before going into the detail for our EPSR, estimated potential scale reduction. So in this case, what we're going to have is multiple chains that are drawn in parallel. So this is chain number 1, 2, up to capital C, okay? Where C denote my chain index. And then for each chain, I'm going to take sample. I'm going to state from starting locations, which are all different for each of my chain. So my first index is my sample number. My second index is going to be my chain number, okay? So, and the superscript B here refer to my first part of sample, which are going to be discarded because they belong to my burn-in phase. Then when the samples from my burn-in phase are discarded, all of these are going to be what I'm going to consider as my stationary sample, okay? Those that were not excluded in the burn-in phase. These are going to be my stationary sample, and in a generic way, my theta SC. The first index S is the sample number, C is going to be my chain number, okay? Where capital S is my total number of sample taken after my burn-in samples. So if we want to look at this estimated potential scale reduction that will allow us to quantify have I converged or not, have I taken enough sample or not, we're going to represent this EPSR by R, capital R at, okay? So the key here is to compare the within chain and between chain variance in my samples. So to calculate the within chain variance, I'm going to first look at the mean or the empirical average of each of my chain, okay? So in this case, for each chain C, the mean value is going to be 1 over S, the number of sample in each chain, where I'm going to sum the samples for each of the chain C. Then the variance estimate I'm going to have, W, is going to be, I'm going to calculate the empirical variance for each of my chain, where the respective mean of each chain is given by my approximation here. And then what I'm going to do, I'm going to take the average 1 over C sum of the variance of each of my chain. In this estimate W here, what you have to see is that it's going to underestimate the true variance of my sample. Then in the second time, what I'm going to look at is what is going to be my variance estimate between my chain. So to do this, the first step is going to be to calculate what is the global average of, or the global mean of all my chains. So what I'm going to do is I'm going to do the average of each mean position for my chain. So 1 over C times the sum of the mean position for each of my C chains. Then the variance of these estimator is going to be 1 over C minus 1, the sum of the mean position of each chain times the global position for all my chains that I've defined here. So at the end, we're going to define a quantity V hat, which is going to be S minus 1 divided by S times W, my estimate I have here, plus B, the between chain variance I've calculated here. And this V hat, its property is that it overestimates the variance. Okay, so my EPSR, R at, is going to be defined as the square root of V at that overestimate my variance divided by W, which underestimate my variance. So keep in mind, W underestimate, V at overestimate my variance for my sample. So at the end, what we can say is if I have a true value for what should be the variance of my samples, V at is going to, as the sample is going to increase, is going to approach it from the top. W is going to approach it from the bottom. Okay, and V should be always greater than W, meaning that when we take that ratio, it's going to asymptotically tends to 1. Okay, and if it's very close to 1, we're going to say we have converged. If it's much greater than 1, so say greater than 1.10, we're going to say we haven't reached the convergence yet. The upper and lower bound are too far apart. Okay, this is what we want to look at in order to quantify have we converged. And when we have a vector of parameter, not only one, we're going to compute one EPSR estimate per dimension. Okay, so let's look at this through some illustrative example. So what we have here on the leftmost plot is going to be my proposal distribution, okay? For theta 1, theta 2, this is my proposal. Given my current location, where could I move next? So, and here I've decided to take 3 chains in parallel to calculate my EPSR. So I start for this location, and this location. So the 3 have randomly picked starting location. So you see that here I've taken only 100 samples. So we see visually that I don't have a correct exploration of my domain. Many parts of the domain are not explored in each chain. So here I don't expect to have reached the stationarity. So here, if I look at my EPSR, my R at, I have 1.10, 1.09 for each dimension. So here I haven't converged, okay? And we can also look at our acceptance rate beta, which is here 60%. It means that 60% of the time I accept to move to my new location. So here 60% is not a great value. I'm not going to be efficient, okay? What if I increase my number of samples? Instead of taking 100, I take 1,000. So we see that my EPSR values for both dimensions has dropped, okay? Now I'm closer to have reached convergence, but here it didn't, adding more sample didn't change my acceptance rate, which remained constant, okay? Visually, I can see I'm better, but I can probably do more. If instead of taking 1,000, I take 10,000, my EPSR dropped further again. And here I can be confident that yes, I've reached the stationary distribution. I've taken enough sample, okay? But no matter how many samples I've taken, my acceptance rate remained constant. What happened if I go back to the case where I have 1,000 samples here? So this is the same example we've seen before, where here the standard deviation of my proposal distribution was 1. Okay, so I reached these value for EPSR, this value for acceptance rate. And now what I'm going to do, I'm going to increase the standard deviation, meaning I'm going to do larger steps. So instead of having a value of 1, I'm going to have a value of 2. So now we see that the acceptance rate went from 60% to 38%. Okay, if I do greater step, I'm going to move farther apart from my current position. The effect of this is that I'm going to, on average, reject more sample, okay? And this was reflected in my now lower acceptance rate. And it has a small but limited effect on my R at here, okay? So we see that playing with my proposal is going to affect my acceptance rate, okay? And here, the closer is our acceptance rate to our perfect target. At the end, the more efficient we're going to be at sampling, okay? In one dimension, like it is here, it is easy to find a good proposal distribution, okay? Because we're only in 2D, we see our posterior, we could easily pick a good posterior, okay? But when we're going to be in 20, 100, 1,000 dimension, it's going to be much harder to find an appropriate proposal PDF, okay? So we're going to investigate what is the criteria we can use to define a good proposal, okay? And then what is the generic PDF for that's going to be self-tuning and that can be adapted to any domain. So let's look at the proposal PDF for a target PDF that is a little more complex. So before, our target PDF was this. So now let's have a target PDF which is highly correlated, okay? And now instead of having 3, I have 4 chains. I have a total for each of my 4 chains, 1,000 samples, okay? This is my proposal distribution. Now my acceptance rate is 17%, and these are my EPSR 1.05, 1.4. So I'm not really good with respect to my acceptance rate. I'm not really good for my EPSR. It's not catastrophic, but it's not really good. We see that for some of my chain, I have really bad exploration for my space. So I would not have deemed I've converged yet. So what could I do? I could take a smaller proposal, okay, going from this to this. So the acceptance rate now is a little bit better. My EPSR, I mean, pretty much the same thing. How can I improve my EPSR by maintaining my acceptance rate? Okay, what if I use this proposal? Okay, so here I have a negative correlation in my target. I'm having a positive correlation in my target. The result is catastrophic. Okay, going from here, look at my EPSR. Remember, I want to be as close as possible to 1. Okay, so 1.05, now at 1.35. Okay, why? Because my proposal is not compatible at all with my target. Okay, I'm going to keep proposing moves that are super far away from the region when I have high probability content, okay? So we can see it from the different chain. The exploration is really patchy and of really bad quality, okay? So what should I do instead? Having a proposal that's going to be compatible with my target, okay? Here by carefully selecting my proposal to have a good target acceptance, good acceptance rate that is within the target, with the same number of samples, now I can reach really low EPSR values, okay? So at the end, what I want you to understand here is that this choice of the proposal PDF is crucial for the speed of convergence and the efficiency of your sampling, okay? So if you want to reach convergence with a reasonable amount of sample, you have to pay attention to your proposal distribution. So, okay, we can say that, yeah, but in 1 dimension or 2 dimension, it's fairly easy to look at my posterior and pick a correct proposal, okay? But keep in mind, we don't want to use Markov chain Monte Carlo in 1 dimension or 2 dimension. We want to use this in 10, 20, 100, 1,000 dimensional domain in order to draw samples, where it's going to be impossible to visualize what our posterior look like. So we need to have an automated way of tuning our posterior for cases that are in more than 2 dimensions. So one way to do this, to have a generic proposal PDF, is to use, again, our multivariate normal distribution, for which the expected value is going to be the current state, and for which the covariance is going to be gamma square, which is going to be a scale factor, times sigma theta star. Okay, where my sigma theta star is going to be the covariance of my target PDF evaluated at its maximal value, okay, at its mode. So we're going to say that my generic proposal PDF is going to be a multivariate normal centered in my current position, for which the covariance is gamma square, a scaling factor times the covariance of my unnormalized posterior evaluated at its maximal value. Where here, my scaling factor is 2.4 square divided by P, where P is the number of parameters I have in my problem. And here, the question, how do I estimate this covariance matrix? Okay, this covariance matrix, what we're going to see next, is that we can have access to it relatively easily using what is called the Laplace approximation that is going to be calculated for the maximum a posteriori value, MAP, for my optimal parameter value, meaning the parameter value is going to maximize my unnormalized posterior. Okay, and such a max, so the maximum of my unnormalized posterior, can be obtained using what is known as gradient-based optimization algorithm. Okay, you can have gradient descent, you can have Newton-Raphson, there are many of them. We're going to cover the basic one here in the next module. Okay, so what we're going to see here is an introduction to gradient-based methods, where we can use the information carried by the gradient of my target PDF in order to climb that target PDF and reach its summit. Okay, so this is what we're going to see with gradient descent. Then we're going to see gradient descent is an gradient-based optimization algorithm that only rely on the derivative of my target function. We're going to see how can we improve over this by using information as well about the second derivative. This is what we're going to see with the Newton or also Newton-Raphson's method. Then we're going to see, okay, how do we obtain those derivatives? We can obtain them either analytically or using numerical derivatives. We're going to look at this. And then we're going to see, okay, what do we do then when we have multivariate domain? Okay, we're going to see a simplified approach, which is to use what we call coordinate descent. And finally, we're going to systematize out once we find the summit of our target PDF or unnormalized posterior, how can we perform the Laplace approximation, meaning estimating the covariance of my posterior PDF. Okay, so first let's untangle the concept of MLE and MAP. So MLE stands from maximum likelihood estimate, MAP stands for maximum a posteriori. Okay, so if we go back to the Bayesian estimation as we saw it in module 3, what we really seek is that full posterior. Okay, the ground truth is this: my posterior PDF for my vector of parameter theta given the set of observation in D. And this is obtained by the product of the likelihood times my prior, this is my unnormalized posterior, divided by my evidence, which act as a normalization constant. In practice, it can be really expensive to calculate this, okay? So instead, what one might want to do is to say, I'm gonna replace that full posterior by only a point estimate, okay? Only the parameter value that are gonna maximize that posterior. How do we do this? I'm going to seek for a single set of parameter value, which are going to be those that maximize that target function, okay? The unnormalized posterior. So here, in order to better, to facilitate the problem, we're going to say, instead of maximizing my function, typically what we're going to say, we're going to maximize the log of the function, okay? So since the log function is monotonically increasing, the max of a function or the max of the log of the function is going to be located exactly at the same place. But here, this is going to kind of flatten the function and make it smoother and make it easier to optimize. That's why in practice, we tend to optimize the log of the functions rather than the function itself. So here we can define, in the context of a maximum likelihood estimate, our target we're going to try to maximize is simply the likelihood, okay? If we want to use a MAP, maximum a posteriori, our target PDF we're going to have, or our target function we're going to try to maximize is the product of the likelihood and the prior, which is here, or unnormalized posterior, okay? So, and in the special case where my prior is uniform over the whole domain, so proportional to 1, we can see that MAP and MLE are going to be equivalent. Okay, so let's start with the fundamental concept of gradient-based optimization. So what we're seeking is that single set of parameter value that's going to maximize the log of my target function. Okay. okay? And we know from basic calculus that the max of a function, it's where at the point where its derivative is equal to 0, okay? So this is our function, the log of our target PDF or target function, and we're seeking for that point or for that value theta star such that the derivative of my function at this value is equal to 0, okay? So we can reach that point or seek for that point using several methods such as gradient descent and Newton-Raphson, okay? Gradient descent is only going to take advantage of the information carried by the slope of my function, and Newton-Raphson, the first derivative and the second derivative, okay? So let's start with gradient descent. So the basic principle is to say, I'm at a current location theta O, okay? And I want to seek for a new location that's going to be higher on my function. So what I'm going to say as heuristic is that the new location I'll propose to move on is my current location plus lambda, which is a scaling factor. You can assume it's 1 for now, times the gradient of my function. Okay, if the gradient is positive, I'm going to move to the right. If the gradient is negative, I'm going to move to the left. Okay, so in that case, where here the gradient of my function, you can see this. Either we put it explicitly with respect to each parameter, to which parameter we will take the gradient, but this is equivalent to the derivative of my function with respect to the parameter. Okay, when you see that nabla sign, it represents the gradient or the derivative of my function with respect to a parameter. So if we want to illustrate this through an example, we have here our parameter space from 0 to 12. The vertical axis is going to be the values for my target function. Okay, this is my target function I want to evolve in, where what I'm really seeking here is that location here. So I'm looking for the location that is somewhere between 4 and 6, for which my target function is maximal, okay? So I'm seeking for this point, and I want to use that gradient ascent heuristic. So if I start from this location here, what I'm going to do is I'm going to move to a next location, which is the current value plus the gradient. So the second graph on the bottom here is the gradient, so the derivative of the function I have here. So I take the derivative at each point. This is what is represented here, okay? So the slope is positive all here, so my gradient is greater than 0. Up to here, this is my max, because I know that the maximum of my function is where the gradient is equal to 0. And the other part here is the part where my slope is negative, up to here. And here I have another min in this case. And then it starts to be positive again, and I have another 0 at my other max. So whenever the slope is 0, it's either a max or a min, okay? So I start from here. My current position is 3.5. My target value is 0.20. My gradient, so the height of my second graph here, is 0.32. So my new location where I'm going to move is the current location plus 0.32, which will lead to 3.5 plus 0.32, 3.82. Okay, and my new target value is 0.34. Perfect. I move to my new location. Then I'm going to do the same thing. I'm here. I look at what is my gradient, 0.56. So 3.82 plus 4.38 and plus 3.82 plus 0.56, my gradient, 4.38. I move there. Perfect. Now I move. I'm here. Okay, good. My current location is 4.38. My gradient 0.76. I move to 5.15. Perfect. Now I'm here, and see now my gradient is negative. So I'm going from 5.15, I'm going to subtract 0.40, I'm going to get a little closer to my max, okay? And I'm going to oscillate like this until I reach the maximum. One of the main issue of such gradient-based approach is that if I don't start in the segment leading to the maximum of my function, or if I take scaling factors lambda, in this case I took lambda equal 1, but if I don't carefully select my lambda for my problem, I might be taking steps that are too big, such that I'm going to miss that maximum and end up in a suboptimal solution on a local maximum, okay? In this case, this would be my global maximum, this would be a local maximum, okay? So if I don't start on the right segment, or if I take steps that are too long, I might reach this suboptimal solution rather than reaching that global optimum. So if we come and now formalize all the steps we've seen with gradient descent, we are gonna start by initializing what is my scaling factor lambda 0, okay? We can start typically with lambda equal 1. Then we have a starting location, theta 0, and we define epsilon, a convergence criteria. When I might stop my exploration. So I'm going to say, as long as the absolute value of the gradient of my function is greater than epsilon, because we know that we've reached a max when that gradient is 0, okay? So as long as the gradient, we're never going to reach exactly 0, okay? But as long as we're above a certain tolerance, we're going to say we keep optimizing. So the first step is going to be to calculate what is my current function value and what is its gradient, okay? Then I'm going to say and to do this, we're going to do those calculations with my value theta old, okay, my current position. Then I'm going to compute where do I propose to move next as my current location plus lambda, a scaling factor, times the gradient with respect to my parameter theta, times my function evaluation at the current value, okay? And then what I'm going to look at is my target value at my new location, the one I propose, greater than at my current location, okay? If this is true, perfect, we move. But if it's not true, we need to adjust our scaling factor. A simple heuristic to make that adjustment for the scaling factor is to say my lambda, that could be initially, for instance, 1, is now going to be lambda over 2. I'm not going to accept to do a full step. I'm only going to do half a step, okay? And then I'm going to go back here to recompute a new position. So until this is not satisfied, I carry on. And once this is satisfied, I say, okay, I'm going to reinitialize my lambda as my initial 1. And my current parameter value is going to be the new one that was proposed. And I'm going to keep doing this until I converge. And then I'm going to say my optimal parameter value is the last one I obtain. And one of the main limitations of this is setting a proper lambda, okay? A proper scaling factor is really difficult in practice, okay? It can lead in some case being inefficient, and some other case really diverging in my analysis. So one way we can overcome this limitation is by using the information carried by the second order derivative of my function in order to calibrate what should be that scaling factor, okay? And this is what the Newton or Newton-Raphson method is doing. So what we have here in this illustrated problem, on the top graph is going to be my target function, okay? This is going to be the parameter space. This is going to be the target value. Then this is the gradient of my function. This is the second order derivative of my function. So here it's a quadratic function, meaning the derivative is going to be linear. The derivative of a linear function is going to be a constant, okay? So the key here is that imagine I'm trying to optimize that quadratic function, okay? I'm at that current location. If I look at the derivative, here the derivative is a straight line, okay? It's a linear model. I know that the max here is at the point where the derivative is equal to 0. So if this is a linear function, I can easily find where is that linear function equal to 0. And this is where I'm going to propose to move. And how am I going to find this position where it's equal to 0? I need to find what is the slope of that linear function. The slope of that linear function is actually going to be my second order derivative, okay? The derivative of my derivative is going to be its slope. And here from this information, I can retrieve at what point does the derivative is equal to 0. So the key here is to build an approximate linear model of my function, of the gradient of my function. So here I'm going to say I'm going to approximate the gradient of my function by a linear function, which is going to be defined by the second order derivative, represented by these two nebulas, times the current value of parameter theta minus theta whole, all the possible value of theta, so this is the theta in my function, minus my current value of theta whole, plus the evaluation of my gradient, so the diamond value I have here, at my current location, okay? So here, what I know is that this gradient, I can set it equal to 0, because by definition, this is where I have my maximum, okay? If I do this, I can now send this value on the left side of the equality, okay? Perfect. I can divide by this value, because what I want is to isolate this. I'm going to divide by this value, perfect. I'm going to send theta old on the other side, okay? So then I say my theta value I want to move next is actually my current theta location minus the ratio of the gradient of my function at my current location divided by the second order derivative. So my second order derivative of my function, the gradient of my gradient. So if we summarize this, my theta nu, where I propose to move next, is going to be my current location minus the gradient divided by the Asian. So if we look at this on the same problem we had before, so we still have on the top graph my target function, its derivative, and its second order derivative, okay? I start with my theta value equal 3.5. Then my target value at this point is 0.2, and I initialize my scaling factor lambda equal 1, okay? So the gradient of my function here is 0.32. The Asian, the 1 Asian or the second order derivative, here 0.63. So here we have to be careful, okay? Here, whenever we're gonna have a second order derivative that is positive, it means that we're currently aiming for a minimum, not a maximum. So in this case, we're here and we see that the linearized gradient function we're building using the information about our second order derivative is the pink line we're here. Okay, so if we just follow dumbly the equation we've defined, the min or the position we're going to find is this position, the position where my linearized function is equal to 0. Okay, we're not moving in the correct direction. Okay, this is because this indicates that I'm in a valley. I'm not going for a summit. Okay, so in that case, what we need to do is whenever the second order derivative is positive, we need to reverse the search direction. So lambda equal minus lambda. Perfect. So now my new location, theta nu, where I propose to go, is the current location minus lambda, my scaling factor, times the gradient divided by my Asian. So 0.32 divided by 0.63. And I take the negative of it. So minus 0.63. So my new position is going to be 4, the position represented here by my pink star, okay? And if I evaluate my target function at that new location, 0.46. Now I'm here, I propose to move where? Okay, I calculate my first order derivative, second order derivative. It is still positive, okay, still problematic. I'm going to take minus 1 or minus lambda as scaling factor here, okay? Perfect, I propose to move there, okay? So now we see that my second order derivative at the next point is going to be negative, but now my Asian or my second order derivative is going to be negative, okay? I don't need to remove my search direction because now my linearized model represented by the pink line really points toward the optimal value. Okay, so it really points to the place where my gradient is 0, where I have the summit of my function. Okay, so this is how it would work. I would move really, really close to my perfect value. So if we systematize those steps for the 1D Newton-Raphson algorithm, I start with a initial scaling factor, could be for instance 1. Then I say I have a initial position for theta 0. I define a convergence criteria. I define what's going to be my target function. Then I'm going to say, while the absolute value of my gradient, with at the end when I'm going to converge, it should be really close to 0. When it's greater than a convergence tolerance, I'm going to compute theta old, so my current value, using my current value, I'm going to compute my function evaluation, its gradient, and its 1D Asian, okay? So meaning the first order derivative, the second order derivative. So if the second order derivative is greater than 0, okay? In that case, I'm going to say lambda is going to be taken as minus lambda. I'm going to reverse the search direction in order to make sure that I'm pointing toward a maximum and not a minimum. Then I'm going to compute my new parameter value as the current parameter value minus lambda times the gradient divided by the second order derivative. Here I'm going to say, okay, I'm going to accept that proposed location only if my target value at the current location, or in this case, my criteria is set in the opposite way. If my target value at the current location is greater than the proposed location, I'm going to say I don't accept to move by a full step, okay? I'm going to correct that step using the heuristic. My length scale or my scaling factor lambda is equal lambda over 2. And then I'm going to go back to the step 6 and recalculate a new position. Then once I've passed this criteria, I say lambda is going to equal to my initial lambda 0. In most cases, we're going to use lambda equal 1. And I'm going to say my current position is the one that was proposed theta nu. And once I've converged over all my steps, I say my optimal value, the one that's going to maximize my target PDF, is going to be the theta star equal to my latest value of theta. Okay. One thing that I've overlooked by looking at all those steps is what about the derivative? How do we obtain them? Okay, how do we compute those first order and second order derivatives? So the simpler solution, if you have access to them, is to calculate them analytically. Okay, so if you have access to analytical formulation, calculate them analytically. This is what's going to be computationally the most efficient. Okay, but you don't always have access to the analytical formulation. It's not always convenient. So in those cases, you might calculate your derivative numerically. Okay, what you're going to do, you're going to introduce a small perturbation in your parameter value, and by looking at the difference in the target values, you're going to be able to approximate these derivatives. For instance, in one dimension, the gradient or the partial derivative of my target function with respect to the ith parameter is going to be approximated by what we have here. So meaning we're going to evaluate our target function at the current value theta plus some perturbation for the ith parameter, meaning that I is an indicator vector, okay? It's a vector of the same length as theta, where it's all 0 except the ith component, which is equal to 1. Okay, and this is going to multiply a perturbation delta theta. So for the first term here, we add a perturbation delta theta. For the second here, we're going to remove delta theta. Okay, this is called the central difference numerical derivatives. And given that we evaluate plus delta theta and minus delta theta, we're going to divide by those two perturbations, so 2 delta thetas. We can do the same thing for the second order derivative. So the second order derivative of f of theta with respect to the ith parameter. So what we're going to do is that we're going to take the difference between the current value plus theta, the current value minus theta. This is my current parameter value, and I'm going to divide by delta theta squared. Okay, if we want to look visually, where does this come from? So what I have on the left term here is my current parameter value plus a perturbation delta theta. What I have on my right hand term here is current parameter value minus delta theta. Okay, so then if we take the difference between the two, so the difference in function here minus the difference in function here, and we divide by 2 delta theta, this is going to be my first order derivative. Then my second order derivative is that I'm going to compute the derivative with respect to this portion, then the derivative with respect to this portion. This is what I have here and there. And then I'm going to divide by the distance between the two, delta theta. Okay, so this is going to be my second order derivative. If I simplify the term, this is going to be the formulation we saw on the previous slide. Okay, so how can we extend this to multivariate domain? Okay, there are general formulation to perform the Newton-Raphson in multidimensional space, which are going to be obtained by saying My new location is going to be the current location minus the gradient of my function divided by its Asian, okay? But the issue while working in these multi-dimensional domain, notably, calculating the Asian might be extremely expensive, okay? So one heuristic that tends to work pretty well is to work with coordinate ascent, okay? Coordinate ascent, what it means is that we're going to evolve, or we're going to explore our multi-dimensional domain as a succession of 1D optimization problem. So in this case, if we initialize our scaling factor, we say that our initial parameter value is given by this vector of parameter. We define our convergence criteria. We define our target function, okay? So here what we're going to say is while our derivative or gradient for a function is greater than epsilon, I keep do my loop here. So here what I say is that for each parameter from 1 to p, so I'm going to do each dimension separately. I'm going to, using the current value of my parameter, I'm going to calculate the function evaluation, its gradient, and its Asian, okay? Then what I'm going to do, I'm going to simply optimize that dimension. Then I'm going to go cycle to the next dimension, optimize that dimension. And I'm going to go like this in loop over each of the dimension. So if we look at this through an illustrative example, this is the target PDF I'm trying to optimize. So I'm trying to reach the maximum. So this plot and this plot represent the same thing. This is theta 1, theta 2, theta 1, theta 2. I'm trying to reach the max here, which corresponds to the max there, okay? I'm starting from this current location. I think it's the blue point, and the red point, I'm proposing to move there. Okay, my current location is 1, for which my function evaluation is minus 4.42. This is my gradient. This is my Asian. So 1D gradient, so first derivative. Second order derivative, and here my second order derivative, note it's less than 0, okay? Since it's negative, I don't need to reverse my search direction. I'm really going to point in the direction of my max. So what you see here is a representation of the plane for which my gradient is equal to 0 and my linearized function representing my linearized gradient for that function here, okay? So what I want to look at is, given the axis x1, I want to find what is going to be the coordinate theta 1 in which that plane, representing the gradient of my function, intersect with the plane for which my gradient is equal to 0. So in that case, that gives me a value of theta nu, being the current parameter value, 1, minus lambda, plus 1, times the gradient, minus 0.06, divided by the second order derivative, minus 0.24. So it means my new point is going to be 0.74. So I move from there to there, okay? And I have a new target value function. Then I was moving initially only with respect to theta 1. Then my second step, I'm only going to move with respect to theta 2. So now you see that my gradient function, my linear gradient function, changed direction, okay? Because now I'm moving only with respect to theta 2. Now afterward, moving only theta 1. 2, and I oscillate here until I reach the summit, okay? I'm going to move one coordinate at a time here. So once I have reached my summit, what I'm going to do, this is where I want to do my Laplace approximation, okay? I want to quantify the curvature of my unnormalized posterior at the summit, okay? Why? Because I want to use the information about these curvature in order to estimate my covariance matrix for my posterior PDF by taking the curvature of my log target function at the summit here. Okay, let's look at how do we obtain this relation between my covariance matrix and the log of my target function. So let's make an hypothesis that our posterior PDF here is a multivariate PDF, okay? That multivariate PDF would look like this, okay? So what I have here, as we see before, this is my normalization constant. This is the exponential of what does look like my bell shape. Then we're going to take the log of that posterior, okay? So the log of that PDF. So these, instead of being now division, is going to be subtraction. The exponential is going to go away, okay, because I take the log of that function. Then I'm going to take the derivative, okay, the first order derivative of the log of my posterior, okay. If I take the derivative of all of these terms, they're not function of x, okay, so they're just going to go away in my derivative. I'm only going to be left with the derivative of what I have on the right here. Then if I take the derivative, this is the formulation I'm going to have. I have 1/2 times 2, so it's simplified to minus the inverse of my covariance times x minus mx. Now what's going to happen if I take not the first order derivative, but I'm going to take a second time the derivative, okay? To take my second derivative, so I take the derivative of this function once again. The result is going to be minus the inverse of my covariance, okay? And this is what is called my Laplace approximation, okay? We can approximate the covariance for my posterior through the curvature, so the second order derivative of the log of the unnormalized posterior. Okay, so with the Laplace approximation, what we do, we make the hypothesis that our posterior is going to be Gaussian. Okay, so we say my full posterior is going to be approximately a normal, where the expected value is going to be our max or map estimate. So we use a gradient descent algorithm to find what is the max of our unnormalized posterior. And then we say the covariance at that location is going to be described by sigma theta star, where my sigma is going to be characterized by the inverse of the negative of my second order derivative. Okay, and these second order derivative are actually described by my Asian matrix. Okay, an Asian matrix is a matrix that contains all the second order partial derivatives for my problem. So this is going to be, in this case, the inverse of my Asian for the negative of my log unnormalized posterior. So I found these theta star using an optimization algorithm. I find my Asian matrix, I invert it, and I'm going to obtain a relatively cheap approximation for my posterior covariance, okay? Where, as I mentioned, my Asian matrix is a square matrix that will contain the second order partial derivative for the log of my unnormalized posterior. So here we can use this Laplace approximation for two things. Either we use this, as we saw before with MCMC, to tune our proposal distribution in the case of MCMC, or if we have some cases where even using MCMC is computationally prohibitive, okay, we have too many dimensions, evaluating our problem is too costly, we cannot afford to do MCMC. In that case, what would we do? As a proxy for evaluating this posterior, we can do that Laplace approximation, meaning we're going to find the maximum of our unnormalized posterior and then evaluate that covariance using the information about the second order derivative. Okay, how do we calculate that Asian? If again we have access to the numerical derivative, we calculate the numerical derivative. If we don't have access to the numerical derivative, what we're going to do is we can calculate them numerically. So if we want to calculate the numerical derivative, what are we going to do? Each term ij in my covariance matrix is equal to the difference between these two terms here. So these two terms, what they represent is going to be here the derivative of my target function as illustrated here. This is my current location, okay? In the first term here, I'm going to move to the right and I'm going to calculate the derivative between those 2 points from a perturbation to the right, perturbation to the top, and perturbation to the bottom, okay? And then I'm going to do the same thing here. The right term I have here is the derivative between this position and this position. And then by taking the difference between the two, this is going to be the difference here, or the derivative with respect to my ith dimension, the one that is horizontal, okay? Where the left term here is what we have here, is basically the derivative between these 2 points. And the right term here is what we have here, is the derivative with respect to these 2 points. Where again, exactly as we had before, that I here is an indicator function, which is equal to 0 for, it's a vector of 0 that has the same length as theta, where only the ith component is equal to 1, okay? Because it means this is only that parameter that we're gonna perturbate. Okay, so at the end, how does it look like? This is an example. My true posterior would be the solid surface here, okay? This is for theta 1, theta 2. My Laplace approximation, which is obtained by finding the max of that function, looking at what are the curvature, and approximating my covariance. If I do this and approximate my posterior by a Gaussian, it would look like the mesh line we're seeing here, okay? So it's not exactly what we have in reality, but it's a pretty good approximation. So to do this, I've calculated what is going to be my Asian for the log of my unnormalized posterior evaluated at the most likely value. And this is the matrix I obtained for my Asian of my log function. What do I do then? I invert this quantity. I'm going to get an approximation for the covariance for my Gaussian posterior here. And here, keep in mind, the closer the posterior is to a Gaussian distribution, the better is going to be the approximation. So in case you would have either multimodal posterior, it's not going to work well. If you have not identifiable problem, so many equally likely solution, it's not going to work well either. So the more it looks like a bell shape, the better it's going to work. If it goes away from this solution, it's not going to work properly. Okay, so now if we do a recap, how do we differentiate between MAP, MLE, Laplace, and Bayes? So we can say that the most general thing we can do is apply Bayesian estimation, as we've seen in module 3, okay? The real ground truth is doing full Bayes. But the problem is that in many cases, doing a full Bayesian analysis using, for instance, the MCMC methods we're seeing here can be computationally really expensive, okay? Because evaluating our target function f tilde of theta might be expensive. It might take a few seconds. If I take a few seconds times 100,000 sample, this is a consequent amount of computational resources, okay? So in those cases, what we can do is resort of not doing a full Bayesian approximation, but maybe doing a Laplace approximation of my posterior, okay? Where I'm going to approximate my theta star using either an MLE, maximum likelihood estimate, so the theta values that are going to maximize my likelihood, or an MAP, the parameter value theta that are going to maximize my unnormalized posterior, that is the product of my likelihood and my prior, okay? So when we have large-scale problem, it is very common that we're going to use MLE or MAP instead of Bayes, okay? Because often Bayes become computationally prohibitive. This is adequate to make the approximation when we have unimodal posterior and when we have large data set, okay? Because keep in mind, when we have large data set, our posterior is gonna shrink and converge to a single value, okay? So if we have a large amount of independent data. But when it's not the case, it's not a good approximation to only use MLE or MAP. We should resort to using ideally an MCMC method, if not possible, at least the Laplace approximation, to take into account our uncertainty in the parameter value for our posterior. Okay, one more issue we have overlooked so far is that in many domain we'll want to explore, either for Markov chain Monte Carlo or for optimization algorithm, is for spaces that are bounded. Okay, it means that are not defined in the real space from -infinity to +infinity. So both the Newton-Raphson algorithm or any gradient-based optimization algorithm, as well as MCMC, by using, for instance, the normal proposal distribution, will have issues if the parameter space you're trying to explore is not unbounded, okay? For instance, if we're trying to obtain the posterior for a mean parameter value, okay, the mean is intrinsically defined in the real space, so it's no problem. However, if we look at a standard deviation, this is defined in only the real positive space. It's not defined to have a negative standard deviation. Same thing for a correlation coefficient. If we want to find our posterior for a correlation coefficient, this is defined in range -1 to 1. And same thing if we were trying to estimate a probability. Probability is only in the range 0, 1. So for all these last three cases, we cannot directly, or at least we're going to be inefficient if we don't take into account for the fact that this domain is bounded. Okay, so a solution to improve our efficiency is to work in a transform space. Okay, theta is our original space, and we want to use transformation function, such as in our transform space, theta is not defined in the real space, so it's in an unbounded domain. So in the case where our original space is already the real space, so my transform space or original space are the same thing. Okay, so this is theta transpose. This is my relationship, so it's a one-to-one linear relationship. So my derivative of my transformation is simply 1. Okay, this is business as usual. We have nothing to do. What if our parameter value is defined in the real space? Okay, in that case, I want to use a transformation such as the log of my parameter. Okay, by taking the log of my parameter, is going to is going to go from a positive domain to a domain that is defined from in the range minus infinity to plus infinity. And the inverse of the function is going to be simply the exponential. Okay, this is what we have illustrated here. We have on the horizontal axis my space theta. The vertical axis is my transform space. So we see that here we only have the valid domain, which is the green region, okay, from 0 to plus infinity. So if we want to transform this positive space in an unbounded space, by taking what's in red here, my log transformation, I'm going in all the possible space, okay? Here I'll need to have access to the derivative of that transformation. Derivative of the log is 1 over theta. The derivative of my inverse function is going to be the exponential. Now, what if we have a bounded range, say from A to B? Then my transformation function can be given by minus the log of b minus a divided by theta minus a minus 1. And we have the formulation as well for the inverse transformation. Okay, we have also the formulation here for the derivative of theta given theta tr or the inverse. Okay, why do we need these derivatives? Is because remember what we've seen in module 1b when we review the concept of probability theory. If we want to define a PDF in a transform space, we need to apply the change of variable rule. Okay, if you don't remember what it is, I invite you go see again module 1b. So here, if we want to solve the problem, what you have to keep in mind is we can, instead of calculating all our derivative, either for the Newton-Raphson or for whatever problem we want to do, instead of calculating all our first and second order derivative in the original space, we're now going to calculate them in the transform space. Okay? So to do this, we can obtain, for instance, the MLE, the maximum likelihood estimate, using either gradient descent or Newton-Raphson, by performing the whole analysis now in a transform space that is unbounded, so that it's impossible now for our algorithm to propose new locations that are outside our valid domain. Okay? So at the end, when we'll find our best parameter value in the transform space, we can simply take our inverse transformation function to see what the equivalent point in our original domain. So here, for instance, we're going to build this inverse function. We're going to encode it so we can directly evaluate our function in transforms or our parameter coordinate in the transform space and transform it in our original space. For the Laplace approximation, what we're going to do, we have to perform it in the original space, okay? Because we're really trying to characterize the covariance of our posterior, and to do this, we need to evaluate that covariance in the original space, because this is where we want to have access to the information. So if we want to apply the same parameter space transformation for Markov chain Monte Carlo, what we're going to do is we're going to define our proposal distribution in the transform space, because all the sampling is going to be done in transform space. So now I'm going to have a proposal distribution defined in the transform space, where my covariance matrix is going to be evaluated in the transform space. So, okay, am I going to do this? I'm going to define a location, which is my MLE in the transform space. And I'm going to define here the log of my target PDF as defined in the transform space. And this is going to allow me to calculate, for instance, using the numerical Asian, my Asian matrix. And then I'm going to say my covariance matrix for my Laplace approximation, my transform space, is going to be minus the inverse of my Asian. So here we have to be careful when we're doing MCMC, because since we're having a space transformation, we need to correct our target function evaluation, okay, to keep the probability content in the now transformed space. So in that case, my target function in the transformed space is going to be equal to my target function in the initial space, but this time evaluated for the theta value corresponding in the original space. Meaning, if I evaluate the inverse transformation function of my parameter value in transform space, this is equivalent to my parameter value in the original space that I can evaluate in my target function. And I have to multiply, remember in the change of variable rule, we say is going to be our PDF, so f of x, times the derivative dx dy in absolute value, or the absolute value of the determinant of my Jacobian. Okay, my Jacobian, remember, it contains the partial derivative of my transformation function with respect to each dimension. So in this case, since each dimension is transformed separately, I can say that the Jacobian matrix is going to look like a diagonal matrix. The determinant of a diagonal matrix is the product of the term on the diagonal. So here my derivative are going to be 1 over the gradient with respect to each of my transformation function for each dimension in absolute value, and I'm going to take the product of this. So this terms I have here is basically the determinant of the Jacobian of my transformation function for each dimension. So in that case, this is equivalent of building ourselves a function that's going to represent the determinant of the Jacobian. So the product of the partial derivative of each transformation function. And then my target function in the transform space is going to be given by the determinant of the Jacobian times my target function. Okay, so if we want to use the same Metropolis algorithm we developed earlier, but this time in the transform space, what we're going to do, the first steps are exactly the same as we had before, except that now we have a transformation function. And now the only place where we're going to have to modify something is then when we calculate our target function, we're going to need to correct by this factor, which is the ratio of the determinant of the Jacobian matrix, calculated either at the current position or the proposed position. And everything else is exactly the same. So let's apply what we've seen together. So both MCMC and gradient-based method to the same case we cover in module 3 about characterizing the strength of concrete samples. Okay. So here what we have is we're going to have several samples from concrete tests, where each sample can be treated as a direct observation issued from that observation model, where Y, the strength I have measured with my press, is going to be equal to the intrinsic resistance of the sample I have plus V, where V is an observation error, described by this observation process or observation error process, which is a normal random variable with 0 mean and variance 0.01 squared. So here my parameters, so if I remind you what were my parameters in module 3, is I want to characterize the mean value and variance for the resistance of my concrete mix, okay, from many samples. So my prior is defined for those parameters. Here in this case, I'm going to define my prior as being non-informative, meaning uniform for my expected value, and 1 over R, this is my non-informative prior, for my standard deviation. So in this case, if I want to define my likelihood, if I assume that the distribution for my resistance is normal with mean mu R and standard deviation sigma R, That means that my likelihood for my observation y, where r, here we assume it's normal, mean mu r, standard deviation sigma r, and v is also normal. So it means my likelihood is going to be normal, mean mu r, because it's going to be mu r plus 0, and variance is going to be the sum of the variance, because here I'm assuming that v and r are statistically independent, okay? If I want to obtain my joint likelihood for many observation, this is going to be given by the product of the marginal likelihood for each of my observation. Now my target PDF that I want to sample from is going to be the unnormalized posterior I have on top here. So the product of my joint likelihood for my set of observation given my two parameter times my prior knowledge, okay, which is here simply 1 over sigma. So here we have to look at my parameter. Mu is defined in the real space, so no transformation needed. However, sigma is only defined for the positive domain. So in that case, for my second parameter, I want to use a logarithmic transformation function so that in my transform space, both mu r and sigma r transform are in unbounded space. And if I want to go from transform space to original space, I simply take the exponential of the value I have. So if I perform Newton-Raphson to find the most likely value for my unnormalized posterior, what I have here, I'm going to perform these steps in the transform space. And the value I found is 43 and 1.8. If I want to know to what coordinate does these correspond in the original space, I take the inverse transformation function. So my first value for the mean remains the same. However, for the standard deviation, I go from 1.8 to 0.6. Now, if I want to calculate my Laplace approximation to approximate my posterior or the covariance of my posterior, I take the Asian for minus the log of my target function evaluated at my MLE value, and I take the inverse of this. This is going to be my covariance matrix evaluated. In this case, this is going to be in my transform space, okay? So this is going to be my scaling factor I'm going to use in order to define what is going to be my proposal distribution in order to perform my MCMC sampling using the Metropolis algorithm, okay? So when I do my MCMC sampling, once I've done it and I have my set of sample, I can compute what's going to be my expected vector, okay, for my posterior. I take all my sample and take the empirical average. So it's going to be 43 and 3.8. Then if I want to calculate my covariance for my sample, I do the empirical covariance calculation for my ensemble of MCMC sample. This is the result I would obtain. Then I could calculate what is going to be my posterior predictive expected value for the resistance. We've defined that the resistance is a normal distribution defined by mu r and sigma r. So what I'm going to do for each instances of sample theta s, I'm going to draw a sample from that normal distribution with mean mu s and sigma s, okay? And for each of those samples rs, I calculate the empirical average. In this case, 42.9, the empirical variance, 40.5, okay? So if I would do this for a set of 3 observations, so my 3 concrete cylinder I broke with a strength of 43.3 MPa, 40.4, 44.8, okay? This represents here my prior, okay? This is a non-informative prior. We have the mean mu r, the standard deviation sigma r, and this is 1 over sigma r. The true value would be the red dot here. This would be my likelihood for 3 concrete sample. And this would be here my posterior, where we see that in this case, I can explicitly calculate and represent my posterior. But what I want you to look at here is how our sample are really representative, where the random walk we did in our domain, the time spent in each part of the domain is really proportional to our target unnormalized posterior we wanted to sample from, okay? In this case, I use 10,000 samples fourth chain. My scaling factor for my Laplace approximation for my covariance matrix is 1.44. My acceptance rate is 0.29, and my EPSR is indicated that I've really converged 1.0009, 1.0017. I'm close enough to 1 to know that I've taken enough samples. And at the end, if I look at my posterior predictive, here I know the ground truth because I know my real parameter value. This is a synthetic example. I know that my real PDF, if I would know the real mean resistance of my concrete and the real standard deviation, would be the blue curve here. And what I obtain as posterior predictive, given the 3 sample I've broken, is more dispersed, is described by the red curve here, okay? So if we summarize what we've seen together, first, MCMC, the Markov in the Markov chain Monte Carlo, is based on the Markov hypothesis, which says that given the present, the future is independent of the past. And that allows us to define a transition model that allows us to up from step to step in the space so that the probability of moving to a new location x at t plus 1 is only function of xt, because we assume from the Markov hypothesis that this dependency on the current time step is equivalent to the dependency on all the previous time step, okay? This is what the Markov hypothesis allows us to do. Then MCMC, what does it allow us to do is to draw samples from the unnormalized PDF. So remember in module 3, when we cover the important sampling method for Bayesian estimation, we knew that the main limitation is that we needed to know, or we needed to calculate the normalization constant, and we saw that it was intrinsically difficult. With MCMC, we go around this difficulty because we don't require anymore to add that normalization constant. So what do we need to do MCMC? We need to define a target distribution, which is going to be the product of the likelihood and the prior. We need to define a proposal distribution. Given our current location, where do we propose to move next? Once we have our sample, what can we do with it? We can calculate our expected the expected value for a posterior PDF by taking simply the empirical average of our sample. If we want the empirical covariance for our posterior, we take the empirical covariance, okay? As here, we can also obtain a posterior covariance. One thing we have to be careful of is that it's going to be sensitive to where we start in our domain, okay? And to avoid the sensitivity to the initial starting value and making sure that we're really having samples that are representative from our stationary distribution, we have the burning phase that we need to consider, meaning that it's going to be conservative to, whenever you're sampling, discard the first half of each chain you're taking, okay? To be sure that you're not going to have influence from the starting location in your chain. Then if you want to monitor the convergence, if I take enough samples, okay, you can measure that using the EPSR, estimated potential scale reduction, okay? And if this tends to 1, you know that you've taken enough sample. Another thing is going to influence your sampling efficiency is what is your acceptance rate, okay? The ratio of how many times you accept to move to the proposed location divided by the total number of samples you've taken. Okay, the target, if you have a 1D problem, is going to be roughly 40%. If you have more than 5 dimensions, it's going to be roughly 25%. Okay, these are not strict guidelines. This is a range. Okay, you want to avoid being below 10, and you want to avoid to be above 80%, for instance. So at the end, we've seen as well that the efficiency of our sampling is really a function of how appropriate is my proposal function for the shape of my posterior, okay? And what we saw is the generic way to tune our proposal in large dimensional domain. It's to assume it's going to be a multivariate normal where my covariance is going to be a scale factor gamma squared given by 2.4 squared divided by p, my number of parameter, times sigma, where this is going to be my covariance matrix, evaluated using the Laplace approximation, where what we do, we're going to use a gradient-based algorithm to first find the max of our unnormalized posterior, and then use the curvature of the log of our target function in order to have a roughly good approximation of our covariance matrix. Keep in mind, this is going to be a good approximation if my posterior looks like a bell, looks like a Gaussian. If it looks like a multimodal function, it's unlikely to be a good approximation. If it's a not identifiable problem, it's not going to work well neither. Okay? Another issue we notice is that if we're trying to take MCMC samples, or if we're trying to do some gradient beta optimization in bounded domain, okay? Our sampling or our exploration of the domain might be inefficient. The trick to go around this difficulty is to transform our exploration space in unbounded space, okay? That's it. Using these foundations we've seen so far, we're gonna be in the next module, module 5, to start to look at machine learning model, notably with supervised learning and regression methods.